Today we are going to be discussing second order coherence theory in the angle degree of freedom. But before we do that, let's look at what we did in lecture number 7. So lecture number 7, we essentially looked at the correlation between the fields at different space points. For example, in this configuration, that's a incoming field, and we were interested in looking at correlation between the field vibrations at location at points rho 1 and rho 2 at z equal to 0. And we saw that we can do this by looking at the field at some location rho at some other z. So the field at u rho at z has contribution from fields at the point rho 1 and rho 2 at z equal to 0. So the field at u rho z is the u rho 1 0, u rho 2 0. There is these factors k1 and k2. These are the geometric factors that depends on the size of the slits that we put here. And this e to the minus I omega t1, e to the minus I omega t2. These are the phases acquired by the field because of the distances that they travel before reaching this point. And if we take the intensity at this point by doing u star u, then we see that the intensity at rho, the spectral density at rho, has contribution from the spectral density at rho 1, spectral density at rho 2, and then this cross term. So this has been the generic way of studying the correlation between 2 points by looking at the correlation at some other point. Okay, then we also looked at the time evolution of correlation function, and for a stationary and ergodic process we found that the correlation function, the temporal correlation function, it follows a wave equation like this. And there are these two wave equations, one with respect to the first variable r1 and the second one is with respect to the second variable r2. And so correspondingly, if we take the single frequency version of this, then we have the cross spectral density function also satisfying this wave equation, which in this case looks like the Helmholtz equation. And this equation is for a single frequency k, omega equal to ck. Okay, then we also looked at the propagation of spatial coherence from a primary source. That we have a source from which the light is being emitted, and we know a certain thing about the source or the cross spectral density at the source, and then with that information we wanted to find out the cross spectral density at a pair of points at some distance away from the source. And then we found that if we know the cross spectral density at the primary source, and if it's w r1 prime r2 prime, that's at this plane, then the cross spectral density at some other pair of points away from the source is given by this equation. That's an integral equation. So w r1 r2 we can find out if we know w r1 prime r2 prime. Now for a completely incoherent primary source, we have that w r1 prime r2 prime assumes this form, that is the spectral density, and there is a Dirac delta function. This basically says there is no correlation between the two separate points. So until r1 prime is equal to r2 prime, this quantity is essentially 0. So this is the definition for the completely incoherent source. And if it's a completely incoherent primary source, then the correlation at a pair of points r1 r2 away from the source is given by this, where this is now a single integral instead of 2, and this is called the Van-Sittert-Zernike theorem. This Van-Sittert-Zernike theorem has a far field version, which is called the far field Van-Sittert-Zernike theorem, and in that case we see that it is the cross spectral density function r1 r2 is essentially a Fourier transform of the spectral density at the source, the primary source, and k the Fourier transform is in terms of k s2 minus s1. So essentially, even if it's a completely incoherent, spatially completely incoherent primary source, one can still get coherence in the far field. So that is the point of the Van-Sittert-Zernike theorem. Okay, so this is what we did in lecture number 7. So now today we are going to study coherence or second order coherence in the angle domain. Now what do we mean by that? So again we start with the same question, similar question, that what is the correlation V star phi 1 V phi 2 between the fields at phi 1 and phi 2, and by phi 1 and phi 2 I mean this. So if this is an aperture, a circular aperture, and if we do a cut here, then the location of this cut is phi 1. If you do another cut here, the location of this cut is phi 2, and it can have certain weight. The separation between these cuts is delta phi. So the question is, if I have an incoming field, then what is the correlation between the field vibrations at a defined vibration at points defined by their angular position or angle? So that is the question here, is what is the correlation V star phi 1, V phi 2 between the fields at phi 1 and phi 2. So how do we find that? Again, it's the same methodology, that we go to certain other point, let's say V phi, away from this this plane, and then we ask the then we, for example, in this setup, if we cut the slits here and then we look at the field at some angle phi at some other location, then it will have contribution from fields at phi 1, phi 2, and of course there will be some geometric factor. And then this is the generic way of answering this question. But again, before we answer this question, let's look at the essential mathematical concept. Again, this will be this is just a repeat of what we did for time and space. We'll do the same thing for angle. So the first concept would be the stationarity in angle. What does it mean? It means the same thing, similar thing, that the mean of the signal has to be independent of the origin of the angle. So V phi and V at 0 should be same, and that's when we call it stationary. In fact, I'm just mentioning what's wide sense stationary in angle. Now, stationarity also would imply that V star phi, V phi, that is the spectral density or intensity at phi, that should be phi independent. That's V star 0, V 0, and the correlation V star phi 1, V phi 1, it should only depend on the variables phi 1 and phi 2 through their difference. So where delta phi is phi 2 minus phi 1. So that is the definition of wide sense stationarity in the angle degree of freedom. Okay, so now just like space and time, in the case of time, the other conjugate basis is frequency. In the case of space, the other conjugate basis is the spatial frequency basis. Now the question is there any conjugate basis for the angle? And if there is a conjugate basis of angle, is there any correlation function in that conjugate basis? So that's the question we want to answer. So the signal we have here, or the field that we have here, is of the form V phi. Now we know that the phi is a continuous variable, but it goes from 0 to 2 pi, and if we increase phi from that, it is then goes as 2 pi to 4 pi, 4 pi to 6 pi, and so on. So it is essentially a periodic function with period 2 pi. Now a periodic function with some certain period can actually be represented like this. That's a discrete Fourier transform. So far for time and space we did continuous Fourier transform, but for a periodic function we have to have the discrete Fourier transform. So this V of phi can actually be represented by through these functions e to the IL phi, and their weightage alpha L, and L goes from minus infinity to infinity. Okay. So right now I'm just saying this is a mathematical thing, that a periodic function phi can be represented like this. This is in the this is the discrete Fourier transform. We will see if such a thing actually exists physically. That we'll see later. But at this point, all I'm saying is that field as a function of phi can actually be represented in a discrete Fourier transform, where in terms of these modes which are of the form e to the IL phi, where L can go from minus infinity to infinity. In discrete steps, so L is 0, 1, 2 up to infinity and so on. Okay, now this can be inverted to represent alpha L in terms of V phi in this manner, and then this is a Fourier transform, but then these the integrals, the limits go from minus pi to pi. So these two form basically Fourier transform, rather discrete Fourier transform, V phi and alpha L. V phi is the field in the angle domain, and alpha L is the weightage of this e to the IL phi components or vectors. Okay, so if this is the field representation, then we can also represent, we can similarly define the azimuthal correlation function, which is this. And if the azimuthal correlation function then can be written like this, where V star phi 1, we are just using this definition and writing it over here. So V star phi 1 is alpha L star e to the minus I L1 phi 1, using different variable L1 here, and then V phi 2 which is alpha L2 e to the I L2 phi 2. Okay. Now again, in all of this, the only random quantity are these alpha. Again, let me mention it here. When we write this for a random signal, this is more of a symbolic thing, because if this is V phi, since continuous Fourier transform cannot exist, so similarly the discrete Fourier transform also cannot exist. So this is at this point is in a symbolic form, but when we calculate the correlation, that's when it assumes a physical meaning, concrete physical meaning. Okay, so this V star phi 1, V phi 2, we write it in this manner: alpha L1 star, alpha L2, these are the only random quantities. So the ensemble average that we are taking is applicable only to this quantity. So we have V star phi 1, V phi 2 written like this. This is just as we did for time and space. There's hardly any difference here. Okay, so now we can write this V star phi 1, V phi 2 just like a cross spectral density, but this time in angle variable. So W phi 1, phi 2, and that we have in terms of a two-dimensional discrete Fourier transform, and this quantity alpha L1 star, alpha L2 we can write as C L1 L2. We can call this orbital angular momentum correlation function. Now why are we calling it orbital angular momentum? That will be clear in a while when we represent how such modes can be realized in lab. So there is a very nice interpretation that goes to this L, which is of the orbital angular momentum. So that's why we are calling it orbital angular momentum correlation function. And once we see that this L is associated with the orbital angular momentum of the photon of the field, then we can see that this Fourier transform is essentially a Fourier transform between angle and orbital angular momentum. But again, at this point it is just mathematical. We'll later see that this L actually assumes orbital angular momentum interpretation, and at that point we can see that this Fourier transform pairing is basically Fourier transform between angle and orbital angular momentum. Okay, so this is the orbital angular momentum correlation function. This is the azimuthal correlation function or angle correlation function. Now for stationary fields, we know that the angle correlation function or azimuthal correlation function has to depend on the angle variables only through the difference. So W phi and phi 2 has to depend on delta phi only. And now if this side depends on delta phi only, then naturally the only way this can be satisfied is that when CL1 L2 is of this form, that is CL1 L2 is equal to some SL1 and this Kronecker delta L1 L2. So when L1 is equal to L2, that's when this is non-zero. If L1 is not equal to L2, this is 0. So that's the Kronecker delta function. Okay, and now if this is the case, then we can write this as W delta phi SL e to the minus I L delta phi. Okay, so this is like the angular Wiener-Khinchin theorem. This we can say this is the generalized angular Wiener-Khinchin theorem, two-dimensional, and this one for stationary fields, this is the angular Wiener-Khinchin theorem, a one-dimensional theorem. Okay. So now back to quantifying angular correlation. So we have a field at this location collected at some angle phi, and that has contributions from fields at phi 1, phi 2, again some geometric factors. Now let's calculate the intensity or spectral density at phi, and again we'll do it in a very similar manner. So V star phi V phi, so it will have contribution from the first term, first slit, contribution from second slit, and then the cross term. So this is V star phi 1, V star phi 1, V phi 1, V star phi 2, V phi 2, and then the cross term. So this one is essentially W phi 1, phi 2, W phi 1, phi 1, W phi 2, phi 2, and then the cross term. And this we can also write as K1 square, this S, the spectral density at phi 1 plus spectral density at phi 2 plus this cross term. We are just repeating here what we did in time and space. It's a very similar calculation and formalism. Now this we can also write as this term as this twice K1 mod K2 mod, and then S phi 1 S phi 2 lambda phi 1 phi 2 cosine argument lambda plus phi k. And here we do the same thing that by writing K1 star K2 star as this, and then this W in this manner, that delta lambda phi 1 phi 2 is this. Then we can replace this W phi 1 phi 2 by this S1 S2 square root, and then lambda phi 1 phi 2, and then the argument of lambda. So again, this is pretty much how we did for time and space. So essentially the point is that by studying the intensity at S, the study is looking at the intensity or spectral density at phi, one can find out the correlation between the fields at phi 1 and phi 2 at some other plane. Okay, now this is the intensity. We can and we can call this a degree of angular coherence. So corresponding to this intensity that we would see, we can define a visibility. Visibility is again S max minus S min over S max plus S min, and this we can calculate to be a quantity like this. If we take the special case where the first term is equal to the second term, that means the total intensity coming from this slit and the total intensity from coming to this slit, if they are equal, then we see that the visibility is simply the degree of angular coherence. So, I mean, this is the same thing we have been doing in time and space. So, if the intensities from these two slits are equal, then the degree of coherence function can be found just by looking at the visibility. Okay. So, now that we know how to calculate the intensity now that we know how to calculate the correlation between phi 1 and phi 2 by looking at the intensity at phi at some other location, and that's the angular degree of angular coherence, and that's the angular correlation function, the generalized Fourier transform. Now, in order to quantify this, we saw in time and space that in order to quantify the correlation function in time, it was always better to kind of look at the correlation in frequency. Similarly, when we quantify the correlation space, we looked at the correlation spatial frequencies. So similarly, when we want to quantify this, it's always more structured actually to look at the correlation in orbital angular momentum or the orbital angular momentum correlation function. Okay, so here we can, just like in time and space, we can have two separate cases. First is when no correlation between different OAM components, and that means CL1 L2 has to have this form. If CL1 L2 has this form, then if you put it in here as a Kronecker delta function, then this is essentially SL e to the IL phi 2 minus phi 1. So we have this is the same Wiener-Khinchin theorem that we retrieved. We can have the second case when there is a perfect correlation between different so this would be different OAM components, and in that case CL1 L2 is alpha L1 star alpha L2. So it is just that the ensemble average is same as the quantity itself. So that's when there is a perfect correlation. Okay, so we have this V phi, the signal or the field in phi, and we saw that this field can be represented as a discrete Fourier transform over modes e to the IL phi. Now the question is, are these e to the IL phi modes, are these physical or just mathematical? So far we have just shown it as a mathematical mode or basis vector. Let's see if it can be physically realized. Okay, so now we go back to the Helmholtz equation that the U rho Z satisfies. Now if we write this this Helmholtz equation, wave equation, in the Cartesian, then it's del square k square U x y z. That's the Helmholtz equation. Now in the paraxial regime, and this we defined last time as to what is paraxial, when W is almost equal to k, that means k is much larger than this Q. And then we also assume that the Z dependence of this UXYZ, this is the field at the monochromatic frequency. So the Z dependence of this field is of this form. That means the fastest variation with Z is of the form e to the I omega Z, and the Z is also there, but that's a very slow dependence. So if UXYZ is of this form, then we can write this Helmholtz equation like this. So in writing this equation, we have used the fact that W is almost equal to k. So when we write this del square, that's del square by del x square, del square by del y square, del square by del z square. And for this del square by del z square, it acts, since we are writing U like this, it acts on both U naught, this part, and then this part. And so we just do the simple calculation, we find that there's a, when del square del z square acts on this quantity, there is it will give out a minus k square term, that will get a minus w square term, that will get cancelled with this k square, and then it also gives twice I omega, which we are twice I w, which we are writing as twice I k. So just a simple math, we can show that this can be written like this. if we assume this form for u and assume w is almost equal to k. Okay, so that's the form of the Helmholtz equation it satisfies. Now with the apply paraxial approximation, then we can also we have that this term is much smaller than this term, and then this wave equation can be written like this, which is, if you don't which can, again we can just write like this. So that's a paraxial wave equation. That's a wave equation, that's a paraxial wave equation. And if you write this wave equation in cylindrical coordinate system, then it looks like this. And this is a paraxial wave equation in cylindrical coordinate. Now, without going through the detail of as to how to solve this equation, I will give some references where this has been solved. But that's a paraxial wave equation in cylindrical coordinate, and one of the solution to this equation is actually called the so-called Laguerre-Gaussian solution, or Laguerre-Gaussian modes. These Laguerre-Gaussian modes look like this. These are function, that's Lg stands for Laguerre-Gaussian, and this is a function of a rho, phi and z, and this has this functional form, and this Lg rho phi z that actually satisfies these this paraxial wave equation. Now we see that this Lg is characterized by these two indices L and P. So that means this L goes from minus infinity to infinity, and P goes from 0 to infinity. So these are two-dimensional modes, and each of these modes satisfy this paraxial wave equation. Okay, now here, I just don't want to go to the details of it, but this we could see this LPL, that's the Laguerre polynomial, and the C is given by a factor like this. Okay, so again, I don't want to go through the details of this solution, and it is actually given in several references, which I will point out when I upload in the notes that I upload. The transverse intensity of these modes, they are, if you just plot the transverse intensity of these modes at any given z, they are like this. So if P equal to 0 and L equal to 0, the mode looks like this. So this is actually called the Gaussian mode, which is when we have a laser beam or laser pointer, that's usually a Gaussian mode. That's P equal to 0, L equal to 0 mode. For P equal to 0, L equal to 0, it's just like a donut mode, and if we increase L value at the given P equal to 0, is just the size of that donut actually just increases. Now at a given L, if we increase P, then the number of rings basically increase. So with L equal to 2, P equal to 2, we have 3 rings here, and that's the solution, and that's the transverse profile, intensity profile of this mode. If you look at the transverse phase of these modes, let's say here I'm looking at with P equal to 0, then at a given Z, it is like this. So for L equal to 0, which is the mode like this, if you look at its phase, it's just flat phase. But for L equal to 1, although the intensity is constant, if you look at the phase, then phase varies like this, and this is from 0 to 2 pi. For L equal to 2, if you look at the phase, if you go from 0 to 2 pi in angle, the phase changes from 0 to 2 pi, and then again 0 to 2 pi. So the phase changes by 4 pi if we go in the azimuth direction by 2 pi. Now this is at a given z. If you look at the phase as a function of z, then we find that the phase for L equal to 0, the phase is constant at every z, but for L equal to 1, it kind of spirals around, and the for L equal to 2, it's a double spiral, and so on. So that's how the phase for these modes look like, and this is how the intensity of these modes look like. Okay, so these are that's the solution for this paraxial wave equation. Here the one very essential point is that we see this e to the minus il phi type term sitting here, and in fact this is the only phi dependence that this mode has. We can see that it depends on z here, there's a rho dependence over there, but that's the only only phi dependence that these modes have, and that is through e to the minus il phi. And we know from this solution that this L is discrete, and it goes from minus infinity to infinity. And then in 1992, it was in this paper that was shown that the orbital angular momentum of a photon in this mode is actually h bar f. So this was a very important result, and this has a lot of implication in quantum information using orbital angular momentum modes. But what this result essentially says that if we, I mean, these are the solutions to parallax wave equation, and if we have a photon, well, we haven't gone into the photon discussion yet, the quantum description yet, but I'm just pointing it out here. So if we have a photon in such a mode, that means if we integrate this mode over enough volume such that the total energy is equal to h bar omega, then for that volume the total orbital angular momentum will be h bar L, and that's what this result says. So this then has the interpretation that a photon in LGPL mode with index L has orbital angular momentum LH bar per photon. Okay, so now let's see if such modes can be. So here, although we started with this e to the IL5 as a mathematical mode, now here we see that these are part of the modes that are physical modes. So now the question is, can these modes be realized in a lab? And the answer is yes, and there are a few methods by which it is realized. The one method is using what's called a spiral phase plate. This is just a glass plate, but its thickness varies as we go in phi. So that's how the thickness varies, and for such a mode, if we send let's say an L equal to 0 phase through this plate, it becomes a kind of a spiral phase, just like this was for L equal to 2, and that's why it's called a spiral phase plate. So the moment it changes the phase to this, it actually can generate, it actually generates the orbital angular momentum mode, and that's the reference where it is actually discussed. There's another method which is using what's called SLM. These are electronic devices called the spatial light modulator. Since this is a glass piece, so this glass piece also generates just a phase, but to generate a different phase, we need a different glass piece. But a phase can also be generated using electronic devices, and the good thing about the electronic devices is for generating a separate phase, we do not have to remove the element. It just needs to be changed electronically. So the detail, I'm not going into the detail of this method, but it's just that there is one can produce a phase like this in a hologram manner, and then for SLM, these are pixelated device, so we can't put the phase just like this in this manner. It has to be in a slightly different format, and with that format, if you send an L equal to 0 beam, it just doesn't become some other L. For example, L equal to 2 here, it gives a different diffraction pattern. The diffraction pattern, the 0th order diffraction remains the same as the original beam, but in the first order diffraction, we see that this L equal to 0 mode gets converted to L equal to 1. And if you put different hologram, let's say corresponding to L equal to 2, then again in this first order, this L equal to 0 mode changes into L equal to 2. So this is one way of generating these L modes, and that's another way of generating these L modes. So there are other methods also for generating these orbital angular momentum modes, but we will not go through that in this course. So here the main point is that this Laguerre-Gaussian modes, they are physical modes that can be produced in the labs, and these are the modes that carry e to the IL5 dependence that we saw in the context of angle when we wrote V of phi, the field in phi in terms of its Fourier transform. Okay, so we will stop here. Thank you.